we're trying to relate electrical field and electrical potential. So the field has to do with mapping the force, while the potential has to do with mapping the energy. So we're trying to get info on force from energy. So let's dive into this. This is how your derivation should start. We're considering electrical field by a point charge Q. So that's your field. And this is located at O. We're considering point A and B, which are at a distance of dr, a small distance dr. So the potential at this point is V and this is V plus dV. So there is a small increase in the potential. Now, the work done on the test charge Q naught, right? We are moving Q naught. Work done on Q naught by external force to displace it. From A to B is given by what? It's given by TW minus of the force exerted by the field on the charge dotted with your dr dot product. So we are equating force that external field exerts should be equal to this as we are moving the charge at infinitesimally slow speed. So acceleration is almost zero. So these two are equal. All of this you guys are familiar with, but yeah, we need to write this in your exams. That's why I'm writing this. Now, we know that potential difference is nothing but the work done on unit charge. And therefore, what do we have? We have the following. And this is nothing but what? That's your electrical field. Okay. Now, dV is on the LHS. What do we have? We have d plus dV. So the delta V is equal to the potential at B minus the potential at A. So this is what we have written, is it not? V and V plus delta V. Small increase in potential. That is equal to minus E or dr. So this and this will get cancelled, right? On rearranging, therefore, minus dV by dr is equal to E. Or, anyways, we can write it the other way around also. So, on rearranging. And this is your relation. What does it tell? That's very, very important. Getting this is not that big deal, but this is what we need to understand. So let me just take a second. Okay, I want to make use of this now. So if I move a charge, right, closer to the field, what happens? For example, let me do this. If I move the charge closer to the field, okay, just a second. Yeah. So if I move a charge closer to the field, the potential will increase, is it not? Agree? While if I move it away, the potential will decrease. In what direction is it pointing towards the electrical field? It's pointing outward. So basically, if I want to increase the potential, what should I do? I should move against the electrical field or towards the electrical field. Again, let me repeat. I have a charge. This is your test charge. Sorry, this is your source charge. This is your test charge. So obviously this is both are positive. That's why we have a push in this diagram. That's what we're considering it as. Now, if I get the second charge, the test charge towards the source charge, what is happening? Just answer that. What will happen? We can see that the force is increasing. So it will have more energy. It has more potential. So it has more potential energy. Now, if I move away, what happens with the potential energy? It will reduce. Can you see that? It reduces. Next question. The electrical field. Is it pointing outward or inward? It's pointing outward, is it not? Right? So, if I want to gain potential energy, should I be moving in the direction of electrical field or against? People who answered in the direction of electrical field, let me show you what happens if I'm moving in the direction of electrical field. So what is happening to the force? It's reducing. So basically it has less potential energy. It's like it's getting closer to the ground. If I have a phone which is closer to the ground, obviously it's much safer. If I have the same device a lot higher, something like this, it's not that safe. So in conclusion, if I move in the opposite direction of electrical field, my potential energy increases. So basically an electrical field is pointing in the opposite direction of rate of increase of the potential difference. If you're looking at if you're walking in a particular direction and if the potential energy is increasing, what can we conclude? It's opposite to the direction of the electrical field. It has to be the highest possible scenario. We'll understand that in time. So let me ask it in this way. In regarding to the direction, electrical field is in that direction in which the potential is steepest. Is it decreasing or increasing? Yes, it is decreasing. The electrical field, if we will be in the direction wherein the potential decreases steep, the steepest value, highest value. Just because it decreasing does not mean electrical field is in that direction. It has to be steepest in that space at that point. Right? Let me give an example. So if I move this now, if I change the value of y coordinate, can you see that? So what's happening? We can see that electrical field is not exactly pointing to the left and right scenario. It's varying. The direction is varying. Right? So to find the steepest is not the same as just having some value. If I see, okay, you know what, if I move in this direction, my value of electrical field is reducing, does not make it the direction of electrical field. It can be in the direction of electrical field, it can be in that particular, minus 90 to 90 degree, but maybe not the steepest. Like you are trying to get down a hill, doesn't mean that we can't get down the hill wherein, you have a longer path and then you get down. This is the steepest. We can have one more path wherein you're reducing, might not be the steepest, but electrical field points in the direction of the steepest value. In terms of magnitude of electrical field is equal to the change in the magnitude of potential per unit displacement. Normal or parallel to the equipotential surface at that given point. This we will answer shortly. Equipotential surface, I have not done that. So answer, let me not tell the answer as well. See guys, this derivation is quite simple. We have pretty much done similar to this, just that one last step we are changing. Two last steps. What you have to take away from here is that electrical field will point in the direction opposite to the steepest increase of potential difference, potential energy. Okay? Or we can tell steep will be pointing in the direction of steepest decrease in potential energy, or it will be opposite to the steepest increase. I hope I didn't confuse you guys. So if it's increasing, electrical field is opposite. If it's decreasing, the electrical field is in that direction. Okay, so yeah, think about it. It's not that hard. It makes sense. You can make use of this, right? If I change the value of, wait, let me make it 0. If I change the value of x over here, as I when I'm going away, the force is reducing. The energy with which it will fall will reduce. If I go closer, the force is increasing, but it's in the direction opposite to the electrical field, right? I hope that made sense. So now it's time for you guys to pause. And this is one of the ways of presenting your answer. There are many derivations, whatever is easy for you guys and whatever your teachers are okay with, please do that. See, I have spelled this wrong. PES. Okay, SIM. Let me redo this. In finite T SIMALLY.